Swayam Prabha. Digital India. Educated India.
So, suppose x star comma y star is a local minimum of is a local maximum in this case of this particular optimization problem. Now, how did we argue in the case when the constraint was an open set? We said, well, x star and y star is a local solution. So, therefore, there is a ball around it and the constraint is an open set. So, what we can do is we can find a ball around it such that the ball lies completely in the feasible region. If the ball lies completely in the feasible region, we said we can move in any particular direction h, and so therefore, and then from there using Taylor's theorem, we concluded that the gradient transpose h should be greater than equal to 0 for every direction h, or less than equal to 0 as the case may be. Okay. So, in that case, then we said that well, one can take h suitably and show that this would imply that the gradient itself must be equal to 0, or the derivative of the function must be equal to 0. So, where does that argument fail here? The argument fails because this is not an open set. So, it is not true that if it just because it is a local minimum, we cannot compare the value of the objective with, we cannot compare that with every point in the neighborhood of x star y star. We have to compare it only with those points that are in the neighborhood and in the feasible region, right. So, you have to be sensitive to the shape of the feasible region near this point, and that has to get factored into your analysis, all right. So, it is not possible to therefore simply work with only neighborhoods, because neighborhoods are not necessarily all included in this. Okay, all right. So, now let's look at a point like this. Suppose x star y star is a local maximum of this optimization problem. Okay. Now, if you look at the so can someone tell me, without loss of generality, can I take either x star or y star as non-zero? So, I did not mention it, but it goes without saying that alpha is positive here. Yeah. So, can I take x star or and either x star or y star as non-zero? Yeah. If both of them are 0, then this equation will not be satisfied, right. So, the origin is not on the ellipse. Okay. So, both of them 0 will not satisfy this equation. So, we will take, suppose let's take for simplicity. So, clearly either x star is not 0 or y star is not 0. Okay. So, let us suppose let y star be non-zero. Okay. So, what that means is, in terms of this diagram here, I am not looking at points where y star can be 0. So, I am looking at points, I am not looking at these sort of points, these 2 points here. These two are points here where where y star could be 0. I am not looking at those points. So, I am looking at only points like these here, either here or here, where y star is non-zero. Now, when y star is not equal to 0, that means we are in somewhere, say, at a point like this. Okay. So let us take suppose this point itself. Okay. So, we are at a point like this. Now, if you are at this sort of point, okay, you are on the surface of the ellipse, and the thing that we want to exploit is, because because you are at this at a point like this, I should be able to, if I tell you what the if I tell you what the x is, I should be able to solve for y in terms of the x, knowing that I am on the ellipse. Okay. Being on the ellipse gives me this particular thing, that if I tell you what the x is, I know precisely what the y is. Okay. So, for example, if this is my point x, then I know that this is what the y is. If this is my point x, then I know this is what the y is. This is because you are on the ellipse. On the ellipse, I can solve for y in terms of x. Now, I cannot do that actually at this sort of point, because here, if I tell you an x here, there are two possible y's. There is a y above and a y below. But here, near the point x star y star that I am considering, I can solve for a y uniquely in terms of x on the ellipse. Okay. So, let me explain this a little more slowly. So, suppose this is my point x star y star, and I look in the neighborhood of x star. In the neighborhood of x star, okay, in the neighborhood of x star, every x maps to a different y and to a unique y, right? And that's so, which means that if I give you an x, I can solve through the equations of the ellipse for what the value of y should be, right? What that's effectively saying is, I can look at this equation f of x comma y equal to f1 of x comma y equal to alpha, and then fix the x here and solve for the y using this equation. And so long as I am not at this sort of point, I should get back a unique answer, right? I should be able to get y in terms of x. Now, this thing which I am just telling you geometrically actually is a theorem. Okay, it's what is called the implicit function theorem. So this is the result of the implicit function theorem. Again, I will tell you what the result is in this particular context. So, the implicit function theorem in this particular context guarantees that there exists an epsilon greater than 0 and opens, so number these, that is 1 an epsilon greater than 0, 2 an open set V containing my point x star y star, and this function g, okay, and a differentiable function g. Will, this function is what will give me back my y in terms of x. That means, the argument to this function is going to be an x and its output will be y, right. So, this function will take argument x. So, but this function will take an x and generate for me a y, but it will generate for me this y in a limited scope, means that only in the neighborhood of x star can I talk of such a existence of such a function. Only in this neighborhood of x star will I be able to get my y back in terms of x. If I make this neighborhood too large, then all hell breaks loose. I get multiple y's. There is no more a correspondence between x and y. So, but so long as I am close enough, I should be able to solve for x in terms of y. Okay, solve for y in terms of x. So, there is a differentiable function g whose domain is like this. It is just x star minus epsilon to x star plus epsilon. mapping back to V. So, in this figure here, V is this open set, okay. X plus minus epsilon is this, sorry, x star plus minus epsilon is this set, x star minus epsilon to x star plus epsilon, okay. And G is the function that, taking a value of x returns a value of y for me. Okay, so now I will tell you what the theorem says. There exists an epsilon greater than 0, an open set V containing x star y star, and a differentiable function G whose domain is x star minus epsilon to x star plus epsilon, mapping back to V, such that if you are on the ellipse, that means if f1 of x comma y equals alpha and you are in this neighborhood V, that is equivalent to evaluating G on that neighborhood. Okay. So, y equals g of x if and only if it lies in the on the ellipse and x comma y belongs to V and is in the neighborhood V that is being considered here, right. So, one direction, it means that if you look at any point that is in the ellipse, that is on the ellipse and in this small neighborhood V of x star y star, then that point can be expressed in this sort of way. Y is a function of x, y equals g of x, okay, and x lies x of course lies in this domain. So, take any point on the ellipse that can be expressed this way. The reverse is also true. Take any x that is in this neighborhood here, evaluate the function, lo and behold you get a point that's bang on the ellipse. Okay. This is what formally it means to solve for y in terms of x. So, you got y as in terms of x. Okay. So, you can actually work this out, solve this as a quadratic equation and get what this function actually is. We do not need the form of it. I just want you to know that this is, we will see how this generalizes. There is such a function, that is the point. All right. Okay. So, now because there is such a function, so now that it means the following, that since x star y star is a local minimum, right, x star y star is the best local maximum, x star y star is the best in amongst all points on the ellipse and in a small neighborhood around x star y star. It has the maximum value of maximum value for this area. So, x star y star is a local maximum. So, let us denote this objective here by f0 of x comma y. So, implies f of x star y star is greater than equal to f of x comma y for all x comma y in a small neighborhood of x star y star and lying on the ellipse. F0, sorry. Right. Now, so in a small neighborhood around x star y star is the best value, gives you the best value of F0. In a small neighborhood of x star y star, y can be solved in terms of x. right. So, if I take the smaller of the two neighborhoods, what must be the case? Both should hold, right? Both should hold. That means there is a small enough neighborhood in which I can solve for y in terms of x as given by the implicit function theorem, and moreover x star y star is the local maximum over that neighborhood. Okay. So, therefore, guys, in a small neighborhood of x star y star, x star, so also the solution of this optimization. Right. So, you can look at this particular optimization in which y has now been substituted for as g of x, and you are optimizing only over x, right. So, so small enough epsilon, the original your x star will also be the optimal solution of this problem. Okay. So, what kind of problem has this become? You have f0, which was a differentiable function. I told you g is also differentiable. So, this is all nice. Your objective is differentiable. But importantly, what is the shape of the constraint? What is the nature of the constraint? It's now an open set, right? So, this is what I wanted to tell you. So, you take a problem where you are optimizing a function over a surface. The implicit function theorem, if it kicks in, lets you convert that to an optimization over an open set over only some of the variables. This was an optimization over x and y to begin with. We now have an optimization over only x. Okay, but the earlier problem in x and y was an optimization over a closed set. Okay. What we have been able to conclude is that it's x star y star, which was the solution of that earlier problem, is also a local minimum of this particular new optimization problem, which is an optimization of a differentiable function, but over an open set, but open set only in x, not in x and y both. Okay. So, now we can simply apply what we know from our previous lecture, which is that this means that the derivative of this new function, the derivative of this thing derivative of this should be equal to 0 at x star, right? And that's just an application of chain rule of differentiation. So, we therefore get that. So, I can write this in the following way, that f0 of f0 x evaluated at x star y star plus f0 y evaluated at x star y star times gx evaluated at x star. This must be equal to 0. What is this quantity? The left hand side here this is simply the partial derivative with respect to x of the function f0 of x comma g of x evaluated at x equal to x star. I have just applied chain rule to get this. Okay. Now, in addition to this, I also have that that the I also have that g of x returns me a point that is on the ellipse, right, in the neighborhood of x star. G of x is a point on the ellipse. X comma g of x is a point on the ellipse. So, which means that x f1 of x comma g of x must be equal to alpha. So, this the first equation comes by optimization, result on optimization over open sets. Over open sets. This here is that x comma g of x lies on the ellipse. Now, for what x does this lie on the ellipse? The implicit function theorem tells you, right? The implicit function theorem tells you that this is true only if you are in a small neighborhood of x star. So, x should be within plus minus epsilon of x star, right. So, this is lies on the ellipse for all x such that x star minus x in absolute value is less than epsilon, right. But then this, since this is true for all x like this that are in this interval from x minus epsilon to x plus, sorry, x star plus minus x star minus epsilon to x star plus epsilon, since this is true for all of them, what does it mean? The left hand side is actually independent of x as I vary x from x star minus epsilon till x star plus epsilon in that open interval, because it's for all these x's it's equal to alpha. What does that mean? What that means is I can put the derivative of the left hand side should be equal to 0, because it's independent of x, derivative with respect to x, right. So derivative at x, so derivative of this at x star must be equal to 0. So, which means that, so that just gives me f1 x evaluated at x star y star plus f1 y evaluated at x star y star, and again g x x star, this should be equal to 0. So, I want to highlight this. We have got two equations like this. Yeah, so this is true for all, this is identically equal to alpha for all x in that interval, right. So, at x star is in that interval, right. The derivative should I mean it's a constant, so its derivative should be equal to 0. If I view this as a function of x, right. So, that's that. Yeah. So that's the reason. So, this derivative must be equal to 0. Okay. Now, what is this f1 of y evaluated at x star y star? f1 y evaluated at x star y star. This is the partial derivative of your ellipse equation, okay, evaluated at x star with respect to y evaluated at x star y star. Okay. Now, so long as my, so if you look at that equation here, so if I take the partial derivative with respect to y, I am going to get a 2y by b square, right, and I had assumed that y star is not equal to 0. So, when y star is not equal to 0, that f1 y evaluated at x star y star is not 0, right. So, since y star is not equal to 0, you get f1y evaluated at x star y star is not equal to 0. Okay. So, what that means is I can just use this equation, second equation here. So, let us call number these, let us call this equation 1, let us call this equation 2. So, I can use 2, from 2 I can just solve for gx of x star. So, gx of x star is equal to negative of f1y evaluated at x star y star times f1x evaluated at x star y star. And this then, putting this into equation 1 gives me the condition that substitute in 1. Sorry, I think I missed an inverse here. So, this is, there should be an inverse here. Now, notice what has happened. So, one of you asked me, we need not know G in closed form. Yes, it is true, we did not know G in closed form, but what I have done is in using equation 2 and using that f1y evaluated at x star y star, this is not 0, I was able to eliminate G from the equation or completely. And I have now got here an equation that is only in terms of x star and y star and the known functions f0 and f1, right. So, this therefore is a necessary, this gives me a new necessary condition for x star y star to be a local maximum. So, go back to the optimization problem that we had, this was the optimization problem. So, x star y star is a local maximum, then it is necessary that x star y star satisfies this boxed equation. Okay. So, what this is giving us is that this is we as a result, by what we have done is we took an optimization of a differentiable function over a surface, use the fact that we were on a surface, use the equations of the surface to solve for some variables in terms of the others, turn that around and substituted and then used chain rule, some more calculus and so on, and then got back a bunch of equations that must be satisfied. You can see that if you did not have constraints, some of these terms would vanish and all you will be left with is just derivative equal to 0. That is all you will be left with, derivative of the objective equal to 0. So, this is how that earlier thing generalized, what we have done earlier generalized. Okay. So, there is the implicit function and this particular term in particular, this term in particular has an important meaning, and I will discuss all these things in the next class. Okay, how this generalizes to more general settings.